Okay, so in this video lecture, and the following two short video lectures, we're going to learn how to take integrals of trig functions. And more specifically, we're going to learn techniques for finding the integral of powers of sine and cosine and tangent and secant. Anytime there's a power involved, we're going to learn to deal with it. And instead of having one long video, I'm going to break up this topic into a bunch of smaller videos, just because, as you can see, this rule here, it takes a lot of space just to write down one rule, and it's just, I figured it'd be different, and hopefully you'll enjoy the shorter videos more. So before we get started, this is section 8.3, and we do need to recall these fundamental identities here. So we have this Pythagoras identity, we have this double angle formula, in a sense, for both sine and cosine, and we'll be making use of both of those. Okay, so the first rule that we're going to, maybe not rule, the first technique we're going to talk about is going to be the case when we have an integral involving sine with an odd power. So that's all this notation here is. So if you're unfamiliar with 2k plus 1, 2k plus 1 is the definition of being odd whenever k is an integer. Okay, so if that looks strange to you, that's all that's saying of being odd. Okay, and when you have an odd power of sine, there's going to be a little factoring that you can do to make your life a little bit easier. And I just remembered that I'm missing one part here to this integral. Let's see if I can fit it in there. So let's see how I got from here to here first, and then I'll feel better. So sine of 2k plus 1 times cosine of n. Sine of 2k plus 1 is equal to, we'll do it in red, this right here, that's equal to sine squared x. And if you raise that to the power k, and then you multiply that times sine x, you will get sine to the power 2k plus 1, right? Here, sine squared raised to the power k is sine 2k, and then you multiply it by sine, you get the plus 1. So that little factoring trick is what you're going to do to move this from that form into this form. So you're basically factoring sine, right? Sine squared to the power k times sine, it's the same thing. And why would you do this? Well, once you have it in this form, you can then replace sine squared by this identity here. All to the power k. And then we have your cosine power n times x, and then you have your sine over here. And I'm running out of room, but you'll see why I'm doing that here. The goal is going to be that we're going to get a integral where we can use one of the integration techniques that we know. So maybe it's just best to go ahead and do the example here. So immediately what I'm going to do is I'm going to factor, I see that the power of sine is odd, so I'm going to factor it like this. So how do I do that? Well, it might help to recognize the form that the power of sine is in. 3 is equal to 2 times 2 plus 1. So that means that k, oh no, sorry, not 2 times 2, 2 times 1 plus 1. So that means that k is equal to 1. Okay. So let's go ahead and do this. So that's sine squared x to the power of 1 and then cosine to the power 4, and then we have our sine x over here. Okay, and now we're going to replace sine squared x with this identity, or actually, not that identity, this one. That'll be more convenient. This identity here would say that sine squared is equal to 1 minus cosine squared. So let's do that. Sine squared x is equal to 1 minus cosine squared x. So and then still have all the stuff out here. Okay. So now what we can do is distribute cosine into this difference. And we can distribute both of these actually. So let's multiply cosine to the power 4 sine x inside, and we will get cosine to the power 4x sine x minus cosine to the power 6 x sine x dx. And then we're almost there. And you'll see like the whole goal here in a moment. After I write this line, you'll possibly see it. Okay. So write this as a difference of integrals. Now, why did we do all this? Well, notice now that we have u du, right? If u is equal to, for example, if we say u is equal to cosine x, then du is equal to negative sine x dx, right? Which means that negative du is equal to sine x dx. So we can take this and write that integral now as something that we know how to integrate. So sine x dx is negative du. So I'm going to take the negative out front. And then we have u to the power 4 du. And then sine x dx is negative u, so we take the negative out and we can do positive. And we have u to the power 6 du. Using just regular old u substitution that we know how to work with. And then we just integrate, right? So this would be negative 1/5 u to the power 5 plus 1 over 6 u to the power 6 plus c. And then what was u? It was cosine x. So that would be negative 1/5 cosine power 5 plus 1/6 cosine to the power 6 plus c. Okay, and then that's the final answer. So the message here is that we have a nifty way of writing this integral as an integral where we can clearly see u and du and then integrate. That's the idea. Okay, and this is the technique that you would use whenever there's an odd power for sine. In the next video, no, actually, I'm just going to pause this video and we'll talk about the other rule when there's an odd power for cosine. Okay, so now we're going to learn how to deal with integrals involving an odd power for cosine. And as with sine, the idea is generally the same. So we have our cosine to an odd power. We write it as cosine squared to the power k times cosine, which just adds up. And then we replace cosine squared with 1 minus sine squared x using the Pythagorean identity. And once we're here, we can multiply out, expand, combine back, and we'll have sine now as our u and cosine as our du, or the other way around. We'll see. So here, notice that we have, with this example, cosine has an odd power, but it doesn't look like cosine times sine. But it really is, we can rewrite this as a product. So power of 6, power of 3. So this is the same thing as saying cosine cubed x times sine to the power minus half x dx. So now it looks like a product. Okay. And we can now write this like that and then use the identity. So let's go ahead and do that. So this will be cosine squared x to the power 1 times sine power minus 1/2 x times cosine x dx. Okay. And then we can rewrite this as the definite integral of 1 minus sine squared x times sine 1/2 x and times cosine x dx. Okay, so now it's really simple. Let's just distribute this in and then write it as 2 separate integrals and see what happens. So we'll do that all in one go. Sine minus 1/2 x cosine x. I'm not writing the limits of integration because I don't have the room. And then what was the other one? So there's a 3/2, sine of 3/2. When you multiply this, sine squared times sine to the power of negative 1/2 is sine 3/2 x. And then we have our cosine x dx. Okay. So, and now we have that, if we let u be sine x, and then du is cosine dx, right? You can see that hopefully that if you just say u is sine x, then du is equal to cosine x dx. So u to the power of negative 1/2, and then du. U to the power of 3/2 du. So then we integrate. So if that's u, that's du. So u to the power of negative 1/2. You add 1 to that, right? And you get a half, and then divide. So 2 sine to the power of 1/2 x for that one. And then for this one, so 3/2 plus 2 is, plus 1 is 5/2, and then divide by 5/2, and it's like multiply by 2/5. So power of 5/2 x. And then the limits of integration are pi over 6 and pi over 3. Okay, so this is going to be 2 times, so power of 3 root 3 over 2. So root 3 over 2 all raised to the power of 1/2. And then this, so sine, so it's still root 3 over 2. Just now to the power 5/2. All minus, now you have to plug in power 6, so that's a 1/2. Okay, so this would be 2 times 1/2 to the power 1/2. That's kind of funny. And then 1/2. Let's see. Where is there a mistake? Something's off. Where could it be? No? No, it is fine. I think I had something wrong with my notes here. Two times, so root 2. So in my notes I have root 2 and then plus root 32 over 80. I don't know where that came from. Where is it? I know pi over 6 is 1/2. So sine of pi over 6 is 1/2 to the power, power 5/2. That's why. That's why. When you plug in a half, so when you plug in a half raised to 5/2, that's how you get these numbers. So no, that's perfectly fine. And for example here, so if I wrote 2 times sine of pi over 6, which is going to be 1/2, right? So this is like saying minus 2 times the square root of a half, or 1 over root 2. And then if you rationalize that, so you see how that's the square root of all of that. So it's negative 2 times 1 over root 2. But then if you rationalize that, then you get root 2 over 2 times 2, and you're left with that. And if you plug in a half and raise it to 5 over 2, so yeah, the half raised to power 5 over 2. That's like taking 1 over root 2. So that's like this piece right there when plugging in pi over 6. It's like taking that and raising it to the power of 5. So that's like saying 1 over 2 raised to the power of 4. You get where is it? In any case, like if you keep on working it out, it does end up being that. And then when you hit it with that, you might have to work it out to make sure that's right. Let me check my other notes. Yeah, that is right. I just feel like it's not the calculus that, like, I don't know if it's worth it for me to show that is that in this little space. Because that means I have to do that. So it's like, another way to think of this is saying, yeah, I'll just work it out just in case you don't see it, just to make sure. So what I'm going to do is I'm going to say this first. Raise 2 to the power 5 on the inside, and then I'm left with the half on the outside. And 2 to the power 5 is, I should just notice something out of my head. So 4 times 2, so 16 times 2 is 32. Half equals 2 over 5 times 1 over root 32. You rationalize it by multiplying by root 32 over root 32. You get 2. You get eventually over there, you get 2 times root 32 all over 5 times 32. So that's 150, that's 160. 160. And then look at that, it works. Yeah, sometimes I miss doing arithmetic-y things like that. I'm kind of happy I did it. All right. So yeah, you see that that matches up with that. And whatever numerical value you get from putting this in your calculator, whatever that number is, that's the answer. Okay. So now I'm going to pause the video and take a look at what happens when neither sine nor cosine has an even power, meaning they both have odd powers. Okay, so now let's look at integrals where both powers are even, and so neither power is odd. Which, by the way, the definition of being even, you don't know. So even means that, so like for example, n would be like 2k for some integer k. Some integer k. That's the definition of being even, and which means that 0 is an even number, and anything raised to the power of 0 is 1. So really, there's a sign in there. There's cosine times sine to the power of 0. So both powers are even. Okay, so as you noticed in both of the previous examples, the goal is to just get a trig function together with its derivative next to it. That's the goal. So that's what we'll be trying to do. So it looks like this is going to be equal to, in order to use that, right, I need to write this as cosine squared somehow. And I can do that, right? I can say cosine squared x all squared dx. And now inside of there, I can use that identity. This is going to be 1 plus, actually, I like to write it this way. Okay. And the reason I like to write it this way is because it's just easier for me to think about when I'm multiplying out or expanding this expression. So we're going to have 1/4, right, and then plus, so 1/2 times 1/2 plus 1/2 times that. plus that again, right? Plus that times itself, right? So it's cosine squared 2x all over 4. Yes. Then we just combine these, right? Combine my terms, which I could have done in one step, but I just wrote it out so you could see it if you didn't see it. So that plus that is 2/4, or just a half. And then all right, so then yes, we can just rewrite this as a sum of integrals. Yeah. So where is it? So we're gonna have 1/4 integral dx plus a half integral of cosine 2x. So far we know how to do all of those. X, and then plus a 4th cosine all squared 2x dx. And that's the only one that's a little bit off. Okay. So the way that this formula works right here, and I say this just to make sure, is that whatever argument goes right there is the thing that goes right there. Okay, whatever is there goes there. Okay, that's the way that this identity works. So we can use that identity again on this, but now we have to put all of that business in place of dx. And I'm going to just write out what that is, just to get it out of the way. I'll leave this one alone for now. And now this is going to be written as 1 plus 4x over 2. Cosine of 4x. Over 2. Yes. Okay, because that's, we put the 2x in as the argument, and then there's a 2 multiplying it. We should be able to integrate this, no problem. So I'll just like scratch mark it right here. If u is equal to 2x, then du is equal to 2 dx, which means that 1/2 of du is equal to dx, which means that that integral right here is going to be written as 1/2 integral of cosine u du. So that 1/2 that we brought out needs to multiply that. And then the integral of cosine u is sine u. And u is 2x. I can split this integral up if I want to. 1/2 dx. So there's the 1/2, and then plus integral of cosine 4x dx. Okay, so then kind of just write it all out. So now this would be x, this would be 1/4 times that, so 1/8 of x. And then if we integrate this, it's not hard to see that you're going to get 1/4 sine of 4x. And don't forget your constant of integration, and when you combine these things, make sure that that's what I got on my paper. Yeah, I kind of figured that was going to happen. I just stopped right there. I don't want to combine these things. There. But realistically, you should, like this. Okay, what would that be? It'd be 3x over 8 plus 1/4 sine 2x plus 1/4 sine 4x plus Jesus to money. And so, okay, that finishes my short video on integrating functions that are powers of sine and cosine. The next one will be on, I'm presuming, tangent and secant. I have to see my notes.